parametric and Cartesian equations with vectors. So we're going to first start off by just drawing up two parametric equations. So we're going to have x equals 2 plus t and y equals minus t. And let's draw up a table of values that describes these parametric equations. So if we do this, we'll have, let's look at just values of t, x and y when t is 0, 1, and 2. The values for x, well, we just sub in t equals 0 and we'll get 2. Sub in t is 1 and we'll get 3 for x, and sub in 2 we get 4. Doing it for y, subbing in 0 we'll get 0, subbing in 1 we'll get minus 1, and subbing in 2 we'll get minus 2. And what happens is, for that one value of t, we get a Cartesian pair of points that can describe an equation. And if you wanted the Cartesian equation, you could just make t the subject in one of the equations and sub it into the other one. So we could make t the subject in our second equation, and we'd have t equals minus y. Then we can sub this value of t into our first equation, and we'll get x equals 2 plus t, which we know is minus y. And we could just make y the subject here, so we'll add y to both sides and then minus x. So we'll get y equals minus x plus 2, which describes the equation of a straight line. So let's graph that out. So we only need our xy axis. So we're going to have a y-intercept of 2 and an x-intercept of 2 as well. And we get the equation of this line with those parametric equations. Now, when we have parametric equations in this Cartesian form, we can actually represent them with vectors. So we could create a vector, let's say r, in terms of t, of some parameter, where all we have to do is take the x components, so which is 2 plus t, multiply them by I, and add in our y components and multiply them by j. So our y components minus t, we multiply that by j, and this vector also describes this line here. And let's see how that happens. So if we subbed in t is equal to 0, we'd end up with the vector, well, when t is 0, we'd end up with 2i. And we can just use our values up here to get our components of 2i, so we get 0j, which is just 0. When t was equal to 1, our x component was 3, so we'd end up with 3i. And our y component was minus 1, so we'd end up with minus j. And when r was equal to 2, our x component was 4, so we'd have 4i. And our y component was minus 2, so we'd end up with minus 2j. And let's see if this successfully describes this line. So let's draw in these three vectors. So the vector 2i is going to look like this. So it describes going from, just has an x component of 2 and no y component. 3i minus j. Well, 3 might be about here, and minus 1 about here. So it's going to be about there. And the vector describing 3i minus j is this. Then we end up with 4i minus 2j, So 4 be about here, minus 2 about here. We end up with this point here, and the vector describing 4i minus 2j gives us this. So you can see just for those three values, we get three vectors where they all end up on the line. So this vector took two parametric equations and we created a vector with them, with the x component and the y component, and it successfully maps out this Cartesian equation of the line with a vector. Let's look at one more example. Let's say we have a vector described in terms of t as 4 cos 3t all multiplied by I plus 4 sine 3t multiplied by j, and we're after two things. We wanted the Cartesian equation. So let's first find that. So if we want the Cartesian equation of a vector, we can just equate the x component to x and the y component for y, and then go ahead and eliminate the parameter t. So if we do that, we'll have x equals 4 cos 3t and y equals 4 sine 3t. We need to eliminate this parameter t. Usually if you have two trig functions, the best thing to do is to square both sides, so we'll do that in both equations. So I have x squared equals 16 times cos squared 3t, and we'll have y squared equals 16 sine squared 3t. Let's go ahead and add those equations together, because we know if we have a sine squared plus a cos squared, it's going to give us 1. So we'll add our left-hand sides together to give us x squared plus y squared. Then we'll add our right sides together. So we'll have 16 cos squared 3t plus 16 sine squared 3t. Let's factorize out 16 on the right-hand side. X squared plus y squared equals 16 outside of cos squared 3t plus sine squared 3t. Now, cos squared plus sine squared of the same angle gives us 1. So all of this is just 1. And we end up with x squared plus y squared equals 16 as our Cartesian equation. And that's obviously a circle centered at 0, 0 with a radius of 4. So let's look at our second part, where we want to find the modulus of R. So all we need to do here is we know that if we want the modulus of R, we can just take the x component squared plus the y component squared, all square rooted. So that's what we're going to do here. So we get 4 cos 3t all squared plus 4 sine 3t all squared. So we get the square root of 16 cos squared 3t plus 16 sine squared 3t. We can factorize out our 16 and we get cos squared 3t plus sine squared 3t. All of this is just equal to 1 because it's sine squared plus cos squared at the same angle, and root 16 is just 4. And we could have got that just from our Cartesian equation, but it was nice to see that it all worked out.